All right. This is Physical Science 102. We're going to look at chapter 22 today. Minerals, rocks, and volcanoes. So we'll start with a share of the PowerPoints. And these PowerPoints, of course, are available in Brightspace. So if you don't have them already called up, or if you just want to follow along with the video, that's fine. If you want to make notes, you need to print out the PowerPoints first, pause the video, come back to it when you've got a printout. And I'm going to make a slideshow. Let's see. Here we go. Now, marker just in case I need one. Minerals, rocks, and volcanoes. Okay, in chapter 21, we studied the Earth's structure, right? All the way down to the core and out, and introduced concepts of plate tectonics. So that was the bird's eye view of the planet. Now we want to drill down, so to speak, and look at rocks and minerals and how they're formed, what they can tell us about the history of the Earth. That's one of our objectives. Okay, what's a mineral? Well, by definition, and your textbook calls a mineral a naturally occurring inorganic crystalline solid. That's important. Consisting of one or more chemical elements. So it can, and most of them are extremely complex. There are very few minerals that we would consider pure substances. They're usually mixtures. But they generally contain these elements in very specific proportions. And they also have distinctive physical properties, which is useful since that's the way we classify them, based upon their physical and chemical properties. They are everywhere, right? You can't walk anywhere without walking across minerals. Some of them are quite valuable, such as diamond. Now, diamond is a pure substance with maybe some added impurities that give it color. But the diamond, a pure diamond, which is made entirely of carbon, if it's only got carbon in it, that is definitely a pure substance. And the diamond, if it has no flaws, is a single molecule. No matter how big it is, if there are no flaws, no breaks, then I could, on the microscopic level, I could stand on one carbon, jump to the next carbon, always across a bond between carbons. I could go from one side of the diamond to the other side and always be in the molecule. Now, if there are some impurities embedded, the diamond will have colors. Sapphires are an example, emeralds are examples. These are compounds. Diamond is an element. It's an allotrope. Which just means it is an element, but it takes a specific form of the element. Graphite is another form of carbon. It's an allotrope. Sapphires and emeralds are compounds. They have more than one element combined to make up the mineral. You may have heard of quartz. Quartz is a mineral. It's primarily silicon dioxide. And when we studied chemistry, Remember the empirical formula. That is the simplest formula that is associated with a compound. That's the ratio, 1 silicon for 2 oxygens to yield a neutral compound. Now, the structure may be different. And that's where the difference in minerals often comes in, particularly with silicate minerals. And when we study minerals, that comes in under the heading of mineralogy. We can also, this is a more an operationally defined term, the term ore. Ore is a mineral, but it takes on a special meaning because ores are enriched in certain types of minerals and elements, and they are economically valuable. That's the key. Ores are economically valuable, but they're still minerals. Iron ore, gold ore, I guess you could say, copper ore, and elements are extracted from these ores and holds a rather substantial economic value. Now, where do minerals get their names? Right? It's always useful to know how to name things so that when you're in conversation with someone else who's interested in the same topic, you can be talking the same language and understand what you mean when you say something. When we say silicate minerals, if I were speaking to another scientist or geologist, they would know exactly what I mean. But other types of minerals are named and reflect very often where they were discovered first, their geographic location, or they may be named in honor of some person. Okay, most minerals are some combination of 1, 2, or more of 8 chemical elements. And now we're talking about those elements in the periodic table. Take those 8 elements and combine them in various ways, and you will have 99.9% of all minerals discoverable on the earth. And these are those elements. Oxygen, that's a biggie. Silicon, aluminum. Right? Silicon, aluminum, oxygen. From my perspective, since I'm a soil scientist by training, silicon, oxygen, aluminum are they basically make up our soils, with additions of some of these other elements. Iron is very common. Calcium is common. Particularly in West Virginia, you'll find lots of calcium just under the sod in the soil because in Greenbrier County, because most of the soils over in Greenbrier County are derived from limestone, and calcium is a major component of limestone. Sodium is common, potassium is very common, and magnesium. So those 8 elements make up 99.9% of all of the elements that are found in the Earth's crust in these mineral structures. Over 2,000 minerals have been identified. At least when this slideshow was prepared originally, there were 2,000. There may even be more now. But what makes minerals different from one another? Well, of course, there's the elemental composition, right? That's the most basic level. There's a certain ratio of, say, silicon to oxygen to aluminum, and that ratio for that mineral is fixed, does not change. Also, the structure, how are those elements arranged inside the mineral? And they could have the same chemical composition, in other words, the same ratio of elements, but they may occur in a different structural arrangement. That makes a different mineral, right? So you can't just say the ratio of silicon to oxygen to aluminum is this, and it's always that mineral. It's the arrangement, the physical arrangement, structure also determines what the mineral is. Fortunately for us, there are about 20 of these minerals that are very common. And if we know these primary 20, then we can describe most of the structures in the crust of the earth. In fact, half of those would give us almost 90% of the Earth's crust. Okay, this is a representation of the relative abundance by mass of elements in the Earth's crust. And notice that oxygen is by far the largest by mass of all components, of all elements in the Earth's crust. Silicon comes next, then aluminum. And then the other, let's see, that's 3. The other 5, let's see, 1, 2, 3, 4, 5. And then we hold out a sliver of our pie for the trace elements in these minerals. And these trace elements can have a significant impact on the properties of the mineral. So don't discount them completely. It's just that those 8 elements make up the most of the mineral composition by mass. Okay, oxygen and silicon are 3/4 composition of all the minerals in the Earth's crust. Quartz, for instance, right? Where do we find quartz? Well, walk on any beach, almost any beach. There are some beaches that are made up of non-silicon components, but most of them are silicon dioxide. And these are quartz minerals. If you have ever opened a geode, you recognize that term. A geode is a rock, and if you crack it open, it's got these beautiful crystal structures inside. That's quartz. Some of them have colors, depending on the impurities that are embedded in them. These, where the majority, where the basic structure of the mineral is silicon and oxygen, these are called silicates. Right. The silicate, of course, obviously derives its name from silicon first. There. And then there's an archaic suffix to this word, ATE. Anytime you see ATE in a chemical name or a mineral name, it's referring to oxygen. And that is grandfathered in from ages past. So anything with ATE on the end of it, you can assume is referencing the inclusion of oxygen in the mix. They happen to be the most abundant form on the Earth's surface, or in the Earth's crust, excuse me. Okay, what are some other characteristics of the silicates? We talked about structure, right? The basic building block. And in chemistry, sometimes we refer to this as the unit cell, the very smallest arrangement of elements that is repeated over and over in the crystal structure. That's the unit cell. And in the case of silicates, the unit cell is the tetrahedron. So you know what a tetrahedron looks like this, like that. It has four sides, and all four sides are equal. And if we put a silicon atom right in the center, then we put oxygens at each one of the apexes. And there's one in the back. Okay? Now, that's the unit structure, but you have to recognize that when it's incorporated into a mineral, this oxygen might belong to another unit cell also. It might be shared. Okay? That's important to recognize because this tetrahedron has a formula like that. It has a charge, right? And typically, chemical compounds are neutral. So what this means is that unit cell has a charge of -4. But when you combine it with other unit cells, then the empirical formula takes over. And the ratio of silicon to oxygen is for every one silicon, there are 2 oxygens. So this silicon is balanced in charge by 2 oxygens. Okay, I hope that's not too confusing. Maybe we've got some pictures that'll help us out. Let's see. Basic building block, the unit cell that I was talking about, this tetrahedron. Within the tetrahedron, you have covalent bonding. In other words, electrons are shared, right? When you worked the chemistry chapters, I hope you didn't forget what you learned there because it's going to be useful to understanding these minerals. Covalent bonding within the tetrahedron. And these tetrahedra can be arranged in almost infinite variety of ways. That's where we get the differences in minerals of, in this case, the silicate minerals. The covalent bonding is definitely between silicon atoms and oxygen atoms. But there may also be sharing of oxygen atoms between silicons. So this oxygen might be covalently bound to this silicon and it also bound to this silicon over here. Okay, so there's your tetrahedron. They do a better job of presenting the tetrahedron there. And you see that these oxygens are equally arranged around that silicon. In other words, they're spread to their very farthest way, and that's good because if we assume that the oxygens are intrinsically charged at a -2, then you want those negative charges as far apart from each other as possible. That minimizes the stress on the structure when you can get like charges far away from each other. Okay, so these silicates can also have incorporated in them aluminum as one or maybe other elements as well. but definitely aluminum is a good bet for most added elements in silicate minerals. These arrangements of those tetrahedra, they can be in chains, they can be in double chains, they can be in sheets, they can be in three-dimensional networks. So let's look at three-dimensional networks. A good example would be quartz. A two-dimensional network would be mica. Right? If you've ever seen mica, the mineral mica, you can slide a blade into it and flake off a sheet of silicates. Okay. How about one-dimensional? One-dimensional would be asbestos. Asbestos tends to form fibers, one-dimensional fibers, like just chains like that. So those are some examples of types of minerals that exhibit these arrangements. Okay, all right, there's mica, continuous sheet. Okay, three-dimensional quartz is good. There's another one called feldspar. Double chain, hornblende, I'm not too familiar with these others. Single chain, pyroxene, and independent tetrahedrons. I left that one out, where the tetrahedrons might be packed together, but they're not covalently bound to one another. Okay, so they have, they're just packed in there with the most efficient arrangement. And you get, an example is olivine. I'm thinking pyroxene might be the one that's found in asbestos. Okay, we're going to get some more detail here. The feldspar group. That tells me that there's more than one feldspar, but they are related. They have a three-dimensional network. Right? So you can see the structure, height, width, breadth. And they happen to be the most abundant silicate minerals on the Earth's, in the Earth's crust. Two basic types, the plagioclase feldspars. So they have oxygen and silicon, obviously. They also have aluminum, and then they also have inclusions of calcium and sodium. And they're a host of different feldspars, and put it that way. Right? There's not just one feldspar. There's not just one plagioclase feldspars. Potassium, instead of having calcium and sodium, we incorporate potassium in the potassium feldspars. Okay. Okay, we have, these are different silicate examples. I see some inclusions of fluoride in there and hydroxide. Right? So this aluminum, silicon, oxygen, and then some hydroxides and fluorides. So you can see that these things get very complex very quickly. But that's not bad news, because it allows us to differentiate among the minerals. And these minerals have different properties. Right? So if we know what to call them, we can infer certain things about their behavior. Okay, other examples. Right, here's an Amazonite. Potassium, this would be a potassium feldspar. And it looks like they're included in the same rock structure with smoky quartz. Okay. Normally, silicon dioxide quartz is colorless. It's clear, translucent. Smoky quartz must have some inclusions of impurities to give it that color. I think that is probably iron. Tourmaline. Let's see, we have sodium, magnesium, there's some iron. So now we're branching out. Are these feldspars? Your guess is as good as mine at this point. I'm not a geologist. But notice that these ratios are fixed for each of the types of mineral. The tourmaline is going to have silicon and oxygen, aluminum, definitely. It's also got iron, sodium, magnesium. There's even some boron in here, and some hydroxyl groups. And this one again is found in the same rock structure with quartz. So here's quartz, and here's your tourmaline. Oh, excuse me. That may not be right. This one, the purple one, might be quartz, and the tourmaline is the bottom part of this rock. I think that's true. Okay, so we can subdivide our minerals into two classes: the silicate minerals and the non-silicate minerals. And by definition, the silicate minerals have silicon and oxygen in them, and the non-silicates are everybody else. Fortunately, only about 10% of the minerals are non-silicates. And they fall into roughly a group of carbonates. In other words, let's see, let's put these up here while we're going. Carbonates, right? That's the carbonate polyatomic ion. So combine something with it, like calcium, right? Calcium carbonate. Same stuff as in Tums, right? You chew Tums for a sour stomach. That's what you're chewing, calcium carbonate. Or we could have magnesium carbonate. Right? These two together are often found in, oh, I painted myself into a corner. Drawing a blank. This is pure calcitic limestone, and you can also find calcium carbonate, magnesium carbonate in other types of limestone. Okay, so let's move on. Oxides. You can have minerals made of oxides other than silicon, right? You could have, let's see, what's a good example? Yeah, I can't think of a good example right now. Oxides, sulfides, these are the most common non-silicate minerals. And you can have pure elements, such as gold, silver, certain types of gemstones that we mentioned earlier. Those are all non-silicates. And very often, silver and copper are found in combination with oxygen and sulfur. Right? So in the ore, you may find silver and copper in particular combined with those other elements. Gold, on the other hand, it's called a noble metal for good reason, because it doesn't form compounds easily. Doesn't mean it doesn't form compounds, but it's very often you find gold as simply inclusions in rock structures rather than as compounds. Okay, examples of carbonates, right? There's our carbonate ion. And there's the types of carbonates that usually occur. I mentioned calcium, magnesium. You can also have manganese carbonate, iron carbonates. This is calcite. It dissolves easily in acidic water. That's how you make caves. Right? Go over to Greenbrier County in that region, and you'll find caves. And they're carved out of the rock by percolating water. Right? Water becomes acid when it falls as rain through the atmosphere and picks up carbon dioxide and turns into carbonic acid. Or as it flows through various structures in the soil level, picks up acids, and they readily dissolve calcium carbonate. In fact, that's one of the tests for carbonate minerals. If you think you have a carbonate mineral, then calcium carbonate, all you need is some about 1 molar hydrochloric acid. And what will it do? Well, it will give you calcium chloride plus water plus carbon dioxide. It will fizz because of that. So every field geologist who is investigating sampling rocks may want to know, is this rock calcitic? Right? So all he does is he takes his little bottle of hydrochloric acid and he knocks off a piece of the rock and sprinkles some acid on it. If it fizzes, he's got a calcitic rock there. Okay, calcite. Right? This is a particular mineral structure of calcium carbonate. And it has some interesting optical properties. If you find a piece like this that is fairly translucent and you put it over something, right, the way that the layers form in there, the light that shines up through will split your image, and you'll see 2 images. Say if you have lay it down over your book, you'll see words across here, and then you'll see another list of words here. Same words. It has that effect. Rhodochrosite, manganese carbonate. That is pretty. And an experienced field geologist can look at these, do 1 or 2 tests maybe, and determine what mineral it is in the field. Okay, let's go. That's carbonates, oxides, and sulfides. Excuse me. So we get a metallic ion bound to oxygen ions. For instance, Fe2O3. That's iron 3 oxide. We can have tin 4 oxide or stannic oxide. Here's an interesting ore, right? Uranium oxide. These are all important ores for isolating tin, iron, and uranium. Sulfides, right? You can form sulfides with iron. These are common. Iron, lead, copper, zinc. I mentioned zinc earlier and copper earlier as sulfides present in the ores. all you have to do is separate them from their sulfide, and you have the pure metal. That 2 is in the wrong place. Pyrite should be like that. Right? Not a superscript, it should be a subscript. And it's often called fool's gold because it has that same luster of gold. But it doesn't take much investigation to determine that this is not gold. Gold as a pure metal is very soft. You could scratch it with your nail, with your fingernail. If you try to do that with pyrite, you may cut your nail off. It's a hard mineral. You can get combinations. Copper iron sulfide, lead sulfide, zinc sulfide are independent, and are valuable ores. Okay, I mentioned earlier that mineral classification is based upon what's the ratio of the elements and what is their structure. Okay, that's true. How do we get at that? Well, one way we get at that structure is physical properties. And the way we get at elemental composition is chemical properties. And this reinforces what I said earlier. Many minerals have the same chemical formulas, but they have different structures, which gives them different physical properties. I mentioned this one earlier, the allotropes of carbon. Graphite and diamond are both pure carbon. They are different structures. Right? So we know diamond is hard. In fact, on one scale, the Mohs scale of hardness, and there's a chart in your textbook. In fact, we may show it in a minute. I'm not sure if we are or not. The Mohs scale, diamond is the hardest naturally occurring mineral at 10. The softest naturally occurring mineral is talc at 1. But you can get softer than talc. Some metals are very soft. Sodium. Sodium has a Mohs scale of about 0.5. So it's softer. Whereas graphite is softer than diamond. In fact, it's often used as a dry lubricant. It's also part of pencil lead, right? Pencil lead is not made of lead. It's made of graphite and some binding agents. Okay. Some types of minerals, you can only identify them with very costly chemical analysis. It's just the nature of the beast. Most of them can be identified with simple tests. Okay. My guess is that if you're training as a geologist, or if you're really interested in collecting rocks, then you will discover that there are, if any of you have had exposure to classification of biological species, very often we use a key, and a key branches. It either is this or is that. If it's this, then you go this way, and it branches again, and it bifurcates in a dual nature, right? So it's either is or isn't. I suspect that similar charts like that are available for mineral classification. So you can say, all right, is it a silicate or is it a non-silicate, right? Branches. Then you go one way and then you just keep branching. So if you're really interested in identifying rocks out in the field, then you want to research this and see if you can get hold of, they even come in kits, field identifying minerals and rocks in kit form. All right, so what are some of these physical properties? Well, what is the structure, the macroscopic structure of your crystal? What does it look like? What's the outward form? The outward form of a crystal structure often tells you something about the microscopic structure. For instance, the mineral halite is composed of sodium and chlorine. You may recognize that as table salt. So what is the structure of halite, or what is the structure of table salt? If you spill table salt on your desktop or the tabletop, take a magnifying glass and look at it, you will see a definite structure there. It is a cube, right? That tells you something about the structure, the microscopic structure of the of that mineral, right? It's got sodium ions surrounded by chloride ions, and then each one of those is surrounded by, and it just goes on infinitely. But the structure that accommodates those ions in that way is a cube. That's a cubic lattice. Okay, let's see. Stay on screen there. Okay, this crystallization can occur fast, occur slow. In fact, most minerals, I would be willing to bet the crystallization occurs relatively slowly. But there's a broad range. And if there's no restriction on space, and you have just the right combination of elements, usually in aqueous solution, not always, but usually, and there's just the right pressure and the right temperature surrounding where they form, then you get a particular crystal form, a structure. And by investigating what that structure is, we can infer some things about how it formed, maybe even where it formed in the crust, deep in the crust, even below the crust. Right, so these are all clues to how these minerals formed. Very often, these individual minerals form in close proximity to the formation of other minerals, right? So it's really a hodgepodge. The proper term is aggregate. So you have an aggregate of different crystal structures, different minerals combined. Perfect crystal structures are rare. Here's a perfect pyrite, iron sulfide. And under the right conditions, it looks like gold, right? That's fool's gold. Here's your halite, fluorite, calcium fluoride, and galena, lead sulfide. Fluoride is a very interesting mineral. If it's properly prepared, it can be made into a lens. And the nice thing about fluorite as a lens is it is transparent to ultraviolet light. Whereas if you make a lens out of quartz, it will absorb the ultraviolet light and only allow visible light through. So I used to operate an instrument called the inductively coupled argon plasma spectrometer. That's a mouthful, but it had a lens in it because the light that came from the hot source, the plasma, had my elements in it, and it emitted light. And I had to focus it through a lens into the spectrometer. Well, some of the wavelengths of light I was interested in were ultraviolet. If I had used a quartz lens, then they would have been worthless. I wouldn't be able to detect them. So the lens was made of calcium fluoride. The physical difference between quartz and calcium fluoride is that quartz is very, very much harder. It's about a number 7 on the Mohs scale, whereas fluoride is much softer. I don't remember the actual value, but it's softer than quartz. So you had to treat it with care, especially when you were cleaning it, so that you didn't scratch the surface. But these minerals have value in places that you might not, that are not obvious on the surface. Okay, what are some of these other physical properties? Let's see, we mentioned hardness. That's a resistance to scratching or abrasion. So if we take the Mohs scale and we say, all right, where does this mineral fit on the scale? Well, you usually have a sampling of 1 through 10 diamond at one end, talc at the other end. And this is one way to do it. And you take your mineral and you try to scratch it with them. And if this one scratches, it's harder. If this one scratches, it's still harder. If you get to the other side and you try to scratch it with this, it won't scratch. Then you know it's between those two. The other way is you use a scratch plate. And you take your mineral and rub it across that and see what forms. And with experience, you can estimate the hardness. Cleavage. What do we mean by cleavage? Well, in geology, we mean the tendency of some minerals to break along distinct planes. Every diamond cutter understands cleavage. You'll see, if you see videos of diamond smiths, those that work diamonds and produce gem quality stones with different types of facets. They start with a raw stone. It's usually smaller than that. And they study it, sometimes for weeks, looking for various possible flaws, how to get the most value out of that single stone. They look for points of possible cleavage. And once they finally decide on how it works, they position their tool in a certain place and strike, and the stone breaks evenly down that plane. That is a certain type of cleavage for that diamond. Other minerals have a certain type of cleavage depending on the mineral. And it gives you a bit of information about what type of mineral you are looking at. Cleavage is often used in the field, right? You see geologists walking around and they have this funny looking hammer. It's got a square head on one side and it's got like a pick on the other side. And they can knock off pieces of rock and they can smack it in their hand and see how it breaks. The underlying meaning for the cleavage is that these represent the points of cleavage, and the planes are related to crystal structure. Where are bonds the weakest? That's where they will break, the cleavage plane. Okay, we do. Okay, here we go. The Mohs hardness scale. There are a number of different hardness scales. Mohs was one of the first, but there are other hardness scales that are used with much more detail. Okay, let's see. There's quartz, and let's see. I was looking for another one. Fluorite. Is that the one I'm looking for? So it's a lot softer than quartz. So that calcium fluoride mineral is much softer than quartz. That's why I had to be careful with it as a lens when I was cleaning it. Other things other physical properties, fracture. When you break the mineral, does it fracture irregularly? Is it randomly broken, or does it have cleavage? Right? It either fractures or it cleaves. If the mineral has no planes of weakness in their structure, that means they don't break in a uniform manner. That gives us information. You know, how are those unit cells put together? Color. Right? Now, there are two ways to investigate color. You can do it simply by visual inspection or comparing the minerals side by side to a color chart with different colors, and you move it until it matches. And then there may be a code associated with it. We use one of those with soils. Soil color is one of the properties of soils, and we do that comparison. Or you can put your mineral or a sample of your mineral in a special device that will measure more accurately the actual wavelength of light that is transmitted and or reflected from the mineral. If you're relying on your vision to determine color, you need to take that with a huge grain of halite, a grain of salt, because people's vision is not the same for every person. That's why we use those comparison charts. That's more reliable in the field. Okay, quartz, for example. Pure quartz has no color, but many colors can be part of the quartz mineral depending on the impurities. So whether it's milky, smoky, yellow, purple, red, orange, pink, purple quartz, as commonly known as amethyst, gives you an indication as to what are the impurities in that quartz mineral. Okay, another physical property is the streak. What is the color of the mineral in powder form? Well, how do you get a powder form? Well, you take the mineral and you scratch it on a special ceramic surface that can reproduce the streak from various minerals. What's interesting is that for intact mineral samples, they may, that's a misspelling. It's not it's may. Sample may exhibit several colors if you just look at the mineral. But if you streak it, you may find that it gives you the same color for these two different visual colors. That helps you differentiate well, these two types of minerals and what they may contain as impurities. Luster. How does the surface of the mineral reflect light? Is it dull? Is it shiny? Does it reflect light in sort of a silvery color, or does it a copper color, or is it a gold color, right? The luster of the mineral. The luster of the mineral can also depend on how it's prepared, right? Some minerals they have a dull luster unless you polish them. And then they give you a different characteristic luster. Often they're differentiated into metallic versus non-metallic luster. The non-metallic luster is dull. The metallic luster is shiny. All right. And in fact, we can subdivide non-metallic lusters into different types. Is it sort of vitreous is another word for glassy. When you understand what glass means, glass is non-crystalline. In other words, the glass that's in the windshield of your car or in your house is an amorphous solid. It does not have a repeating unit cell structure. As a consequence, light behaves differently in that than it does in a pure crystalline solid. Adamantine, that's diamond, is an example there. Pearly, right? If you've ever looked at pure opal or an opal gemstone, you understand what pearly means. Some beautiful paint jobs on some high-end cars have this pearly luster to them. Greasy, I'm not sure why it's called greasy. Talc, talc's a kind of a powdery substance. Or earthy or dull, which is characteristic of clay. Here's a streak. Hematite. Hematite is iron oxide, and it gives you that characteristic streak. Notice that the color for the hematite is different than the streak. So the streak is a result of forming a powder on the surface of that ceramic plate with the mineral itself. We mentioned lusters, all right? Here's pyrite. Iron sulfide, excuse me, brain farts, has a metallic luster, whereas limonite is non-metallic. Okay. Other characteristics, physical properties, specific gravity. We know what density is, right? We learned that early on in the course. In fact, probably in the first semester. Density is mass per unit volume. Okay. You can define density for a mineral, but more often it's reported as specific gravity. So this would be the density of your mineral. But what's the density of water? Mass of water divided by the volume. The density of water is roughly 1 gram per cubic centimeter. So most minerals are more than that, are more dense than water. Right? So whatever that happens to be, you ratio the density of the mineral to water. So it's roughly, the specific gravity is roughly equal to the density. Not exactly, because this is not an exact number either. But that's what specific gravity means. It's the ratio of the weight of an equal volume of pure water, the weight of the mineral ratioed to an equal volume weight of pure water. Specific gravity. So specific gravity is a ratio of these two values, right? The units cancel. Specific gravity is a dimensionless number because it's a ratio. Many minerals have a specific gravity 3 to 4 times that of water. Right? So if you threw them in some water, what would happen to them? They sink, right? If the density is greater than water, it sinks. If it's less than water, it floats. Most minerals have a higher density, specific gravity than one. There are a few. Let's see, there's one pumice stone that has incorporated lots of air, right? It forms from volcanic activity that floats in water because of that entrained gas. Galena, lead sulfide, has a specific gravity of 7.6. It is extremely heavy. Pure gold is even denser than that, 19.3. Okay, so this is a table incorporating properties that help us identify minerals. It's just there for your information. Okay, now we've talked about minerals. What's a rock? We have an intuition about what a rock is. It's definitely natural. It's always solid. And it's nearly always an aggregate of one or more minerals. Most rocks are not pure minerals. Most of them are aggregates that combined more than one mineral together. Okay. So when we're looking for minerals, we generally have to go through rocks. So you pick up a rock and you might smack it with your hammer, break it open to get a fresh surface, and then look at it with your magnifying glass, and you'll see a mineral here and a different mineral there, mineral here, several different minerals that have certain characteristics that you recognize. Now, at a distance, you usually won't see those separate minerals. Sometimes you do, but not always. The individual minerals, you have to look down closer with magnifying glass, and sometimes you have to use a special instrument to sample individual parts of that rock for its mineral content. Okay, rocks, here's the fun part. Rocks can be divided into 3 major types, depending upon how they formed. Right? Igneous rock. Igneous rocks are formed from molten form, liquid form, and then they solidify. So the starting point for all igneous rocks is liquid. Now it might be really thick liquid, but it's still liquid. And then when they cool, they solidify into igneous rock. Right? The name of the liquid is called magma. This is molten rock material that originates deep in the earth. And these rocks, igneous rocks, are formed when the magma cools and solidifies. When the rock forms beneath the Earth's surface, we call these intrusive igneous rocks, usually because there's surrounding structures in the crust or parts of the mantle, and the magma is pushed up. It intrudes into the surrounding material, and then it stops and cools and solidifies into that igneous rock. So it's intruding on surrounding forms. Whereas lava is molten rock that reaches the surface of the earth, right? It's expelled, usually in volcanic eruption. So you have two forms of liquid from which igneous rocks form: magma, which stays below the surface, and lava, which is expelled to the surface of the earth. And these are entirely different environments from which igneous rock forms, right? So magma might start out and lava might start out as exactly the same composition. But because magma cools underneath the earth, and usually a lot more slowly, it will form a different mineral or different mineral types. Whereas lava, when it reaches the surface, air pressure is different, pressure on it is different, temperature difference is different between the lava and the environment. It will usually cool faster and form different mineral structures. These are called extrusive igneous rocks. So magma always forms intrusive, lava always forms extrusive igneous rock. It's extruded to the surface, onto the surface, and whatever. So it could flow onto the surface and solidify, right? The Hawaiian volcanoes do that. Or it could be explosive, like Mount St. Helens. And the lava could be expelled under extreme pressure and blown into the air and solidify before it hits the ground. That forms a different type of extrusive igneous rock. Okay, here's solidified magma. So why is it at the surface now? Right? I thought it's supposed to cool underneath the surface. Why do we see it on the surface? A little process called erosion. It used to be deep under the surface, and weathering at the Earth's surface stripped away the surface layers and exposed that solidified magma. That intrusive rock now is on the surface. Right? Here's lava. I mentioned the Hawaiian volcanoes. It looks different, doesn't it? Completely different appearance because it was extruded and then solidified. Okay, the second type of rock forms from a process called sedimentation. Right? These sedimentary rocks are formed usually very near the surface of the earth, and very often, not always, but very often, the particles that form the sedimentary rock are transported with water. They can also be transported with wind, but they're deposited usually in layers. And then as the layers build up, pressure on the lower layers increases, and you can get miles of accumulation above rock. And once you build up that massive pressure, you tend to cement those pieces together and reform the structure of in a process called compaction and cementation. You cement the particles together, and that gives you a new kind of mineral. Okay, so what are the sources of these particles that are compacted and cemented together? They can be rock fragments, right? You can erode pre-existing rocks at the surface. The wind and water can strip away small particles and then blow them away or wash them away to a new location and settle out again to start forming a new sedimentary rock. Right? You can precipitate chemicals from solution. Right? I think this was covered in the chemical chapters, but if you have a solution of various positive ions and negative ions, right? Cations and anions. And they behave in such a way that when they combine, they no longer dissolve in the water. Then they precipitate. They fall out as a solid. And if that happens, then they settle to the bottom and they build up layers, and you have compaction and cementation of those precipitates. You can also have remnants of plants and animals. Their dead remains form fossils. Now, these are not, strictly speaking, formed from pre-existing minerals, right? But we include them here because they make up an important part of rock structures, such as plant compaction to form coal. Coal's considered a rock. It's formed of basically a carbon matrix of long dead plants and some animals, but usually plants. Okay, there's an example of sedimentary rock layers. You can see the layering here. That's typical of sedimentation, right? So what does that tell us? We said in the beginning that if we pay attention to how these minerals and rocks are, their physical form, their chemical and physical form, we might be able to infer something about the Earth's history. In this case, the inference is that these were once laid down in layers. These are sedimentary rocks. Now, they more than likely were at the bottom of an ocean or a lake or a sea of some kind. Not always, but usually that's the case. So when they're way up here high, something happened to get them there, right? If they formed way down under the water, sedimentation compacted them, cemented them together, then what has happened? Well, the inference is that something, geologic process, lifted them up. And as it lifted them up, gravity and wind and water eroded them away. So now they're exposed. The last form, remember 3 forms: igneous, sedimentary, metamorphic rocks. Metamorphic refers to changing rock. It's already rock, we're going to change it. So you take the pre-existing rock, and usually under high pressure, temperature, and maybe even some chemical changing going on, you change a pre-existing rock into a new form of rock. And that usually involves the change of the mineral that's included in the metamorphic rock. So it might have the same ratio of elements in the metamorphic rock from its parent pre-existing rock, but now we've changed its structure by pressure and temperature. And sometimes, well, there's usually a chemical change also. That's metamorphic rock. Metamorphism generally occurs far below the surface of the earth. You need high pressures, high temperatures to get this to happen. It's sort of in the middle range, right? If you go too deep, then you get so much pressure and heat that you melt the rock. Now you're going to make igneous rock, right? It's not metamorphic anymore. But if you go not quite that deep, not too shallow, not too deep, Goldilocks, just right, you get enough pressure and temperature that you can change pre-existing rock into metamorphic rock. Here's an example of metamorphic rock. And very often what you'll see with metamorphic rock is it's been twisted and bent and formed rather than cracking, which does occur, of course. But if the pressure and temperatures are high enough, then you can get the rock as it forms to soften somewhat. It's not liquid, but it can be sort of plastic. And if the pressures go a certain way, the rock goes with it. So you can get these curvy structures. This is metamorphic rock. Okay, let's look at some history. Some historical facts, and see what they can help us with understanding the formation of rocks and earth processes. Early on, before about the 19th century, most scientists thought that all rocks were deposited by the Great Flood. That was just common knowledge. And we often refer to that these days as the young Earth theory, that the Earth is really only about 6,000, 6,500 years old. Then, well, they also considered other types of catastrophic events that contributed to the present form of the Earth. All right, we're not going to spend any time on these because we want to look at the history of geology, how our understanding has developed over the years. All of these ideas are grouped together in one form or another and called catastrophism. In other words, a catastrophe produced things the way they are. The competing idea developed in the early 1800s called uniformitarianism. Now, this idea was proposed by actually he was a physician, he was a doctor, but he was also an amateur scientist named James Hutton. And he lived in Scotland. In fact, a lot of scientific advances came out of Scotland. This is just one of them. He would go on long walks in the countryside. And if you've ever been to Scotland, or at least seen pictures of Scotland, you'll see that the terrain in Scotland is varied. It's widely different from the south, particularly from the south to the north. And they have some pretty high mountains. They have some caving. They have some erosion that exposes certain types of rock layers. So he used to go out and just visit the countryside, and he was interested in these rocks. And he developed this idea that the key to the past, in other words, how the rocks formed, Earth's history, the key to the past is the present. That's uniformitarianism. In other words, whatever's happening now happened in the past also. So if we could get a handle on how things are happening now, maybe we can deduce what happened in the early history of the Earth. Okay, and there's a formal definition. Geologic processes that occur today also operated in the past and can help us explain certain events that occurred in the past. All right. So what James Hutton proposed was that rocks in the Earth's crust are continually being formed and broken down and reformed. These processes have been going on for a long time. That was one condition. In order for us to infer things about the past, we have to assume that the Earth is not young, that the Earth is very old. And the processes we see today, sedimentation, the metamorphic part is a little difficult to deal with because it occurs where we can't see it. But igneous forms, right? We see volcanic forms, right? That gives you some clue as to these rock forming processes. This is often grouped under the big tent of the rock cycle, right? How do rocks get to be where they are, right? And you can go through various cycles. You can form sedimentary rock, and then it can be metamorphic, and then it can be melted and form igneous, and it can just go in a cycle, or you can cross cycles. This is a general term that covers all of those processes. And that's a more concise way of saying just what I said right there. Okay, so we can break these processes down into various subsets to try to get a handle on what's happening. Right? I tell my chemistry students all the time, nature just does what it does. Right? It would do the same thing whether we were here or not. What we try to do is to categorize, organize, try to rationalize, understand how things are happening. And one of the ways we do that is to classify various processes. One is deposition, right? Particles in some processes have to be deposited. They have to come in, settle out. When they do that, they had to get there somehow, right? We transported them. Nature transported these particles somewhere, or even transported lava somewhere, right? So we transport and deposit. Maybe the rock's already formed, and we're going to weather it, right? So what are some weathering processes, right? Water can wash away rock over time. Wind picks up particles and blows them against rock and chips off pieces. Or freeze-thaw cycles, right? You develop little cracks in the rock. Water gets down in there, freezes, and what does water do when it freezes? It expands, and it cracks the rock surface. Over time, flakes off more of it. That's weathering. You could even melt it, right? That would have to occur deep in the earth. You can crystallize, right? In the process of metamorphism, you can form new crystal structures, right? Or you can form precipitates. That may be a separate process. Let me see. Okay, crystallization. We can include precipitation in crystallization. Then these particles, maybe if they're sedimentary, you have to cement them together, right? Make them stick together. Compact them under pressure. Pack them down hard. You can even get hydrothermal effects. These are usually processes of dissolution. That is, hot water can be injected into, think of Yellowstone, right? Yellowstone has lots of hydrothermal vents that come up as geysers. Well, they don't have to be geysers, but this hot water is able to dissolve minerals from the rock more effectively, right? Higher temperature means more solubility. So it can take the rock and dissolve it and send it someplace else. Those are a few of the processes. This is a representation of rock cycle. Okay. So you can see we've got sedimentation occurring up here. And then if it gets buried and cemented and compacted, we can form sedimentary rock. We can weather it and go back up to the same cycle, back up to the starting point. Or we can heat it under pressure and metamorphize it. We can melt it. Now we're going to make igneous rock. We can cool it as an intrusive rock, or we can blow it out the top as lava and form igneous rock. Right? Or you could even take igneous rock and heat it under pressure and metamorphose it. Right? So that's possible. You can take once molten rock that's now solid, put it under pressure at the right place in the earth, and change it again. It's more, rather than a cycle, it's more like a rock web. Okay, so I mentioned part of Hutton's proposition was that if the key to the present, or the key to the past is the present, then it's obvious that these processes have to occur over very long periods of time, millions and millions and millions, billions of years, some of them, in order to account for the present day forms that we see in the rocks. Okay, so present day geology depends upon uniformitarianism. They reject catastrophism almost completely, not all the way, because there are certain types of catastrophes that can produce different rock forms, right? Meteor strikes, for instance. When a meteor strikes the ground, it has enormous amounts of energy. So when it hits the ground and stops, where does that energy go? Well, it usually turns into heat. And that can change the structure of rocks around it. It can even change the structure of rocks inside the meteor. So catastrophism is not totally denied by present day geologists. Just most of their theories revolve around uniformitarianism. They also believe in the rock cycle. These three types of rocks can interchange among one another in various ways. The rock web. And they also have to assume that the Earth is very, very old. Okay, so when we talk about igneous rocks, right, we've already mentioned how they form. You need molten material. That's prerequisite. It has to be liquid. It could be magma, right? Beneath the earth, molten rock underneath the earth. Or it could be lava escaping to the surface of the earth. Most geologists think that the first rocks on the earth were formed as the outer crust slowly solidified over time. So they believe that in the beginning, the Earth's crust was almost exclusively igneous. And we're talking about, let's see, what is it? 4.6 billion years ago was believed when the Earth first formed. Actually, when the planets formed from the solar system. Since then, various geologic processes have modified them, have covered up most of the former rocks that that formed when the Earth cooled. There are a few, we can find some that we think are the oldest, but they've not always been on the surface. In other words, they had to be, erosion had to re-expose them. I get this. Most of the Earth's surface is believed to be 80% igneous. That's a lot. Now, my guess is that a large portion of this igneous rock is under the ocean. That's what I'm guessing. Two basic types of igneous rock. We mentioned these earlier. Extrusive igneous rocks, those that come to the surface and cool, and intrusive, those that break into structures above and sit there underneath the surface of the earth and cool. Right? Those are the two major divisions of igneous rock. And we only see those if they are further pushed up or eroded away. Now, the main difference between these two is how fast do they cool. Intrusive rock cools slowly. It's surrounded by other rocks. So it doesn't give up its heat as fast. Whereas rock that, lava on the surface of the earth cools much faster. So that means it forms a different structure. It's a different mineral structure. Two basic classifications help us distinguish igneous rocks. One is texture. What are the size of the mineral grains in the igneous rock? And very often you need microscopes to tell you that. What are the size of the particles, the grains, the crystals inside the igneous rock? That's texture. And then what are the specific minerals that are in the igneous rock? As we said earlier, that most rocks are a conglomerate of several minerals. So these two give us the lion's share of information that we need to classify an igneous rock. All right. What does the cooling rate have to do with texture? The slower the molten rock cools, the larger the grains. Right? The faster it cools, smaller the grains. That refers to the cooling rate. Right? Let's see. This is not a rock example, but if you put fresh food in a baggie, stick it in the refrigerator, actually in the freezer, and let it freeze, it freezes slowly. That means ice crystals that form inside the food, in the cells that are part of the food, are big. And as they grow, they rupture the cell walls of the food. So many foods don't like that. When you thaw them out, they're nothing but soupy, right? Because you've ruptured all the cells and now the liquid comes out and makes a mess. Okay? So one way around that is to freeze them very fast. If you freeze food fast, ice crystals are very small, so small that they don't rupture the cells. Quick freezing, right? You can do that in a blast freezer at minus 40 degrees Celsius. Or you can, as a scientist, I used to quick freeze plant samples in liquid nitrogen, right? At minus 195 degrees Celsius. Very fast freezing, very small crystals. It preserved the integrity of the material. So that's an illustration of speed of freezing and what it has to do with the size of the crystals. Similar processes happen in rock. So if it cools fast, small crystal structure, cools slow, large crystal structure. This rock was part of Mount Rushmore cooled very slowly. And you can tell that because all you have to do is chip off a piece or just go down to this area down here, the tailings from the sculpting, and just pick up a piece of it and look at the crystal structure with your microscope. And you can see that the crystal sizes, the particle size is very small. Oh, here they go. They're going to show us. This is a surface of granite from Mount Rushmore. It shows small crystal structure. And you have different minerals too. You can see these darker minerals and the lighter minerals, different colored minerals, lots of different colors. So we know that there's more than one mineral in there. Okay, so these are examples of types of igneous rock. Intrusive, so it bulges up into the underlying layers, but it doesn't reach the surface. At depth, cools very slowly. Oh, my mistake. I correct myself. These are large grains, large crystal grains, because this granite cooled very slowly. I misspoke earlier. Not small grains, large grains when you cool slowly. So the texture would look coarse with very large grains. And we typically, example is granite. Granite forms underneath the earth. It's intrusive igneous rock. Extrusive. So expelled to the surface, cools rapidly, forms very fine grains. Basalt is an example of that. Let's see. This forms on the surface or underwater, actually. Whereas this one, an extrusive rock in air or water, cools very rapidly and forms a glassy texture, obsidian, right? If you've ever seen obsidian, it is very shiny. And in fact, obsidian cleaves very well and can make very sharp edges. The color of an igneous rock can give you a clue as to its composition, right? The amount of silica within an igneous rock. Can give you another clue as to how to classify that particular igneous rock. If the magma or the lava, right, they can form, either one can form from the same source. If it's high in silica, silica minerals with abundant, obviously silicon, but sodium and potassium, these minerals are usually light in color. Okay. Whereas if it forms with less silicon and more iron, magnesium, calcium, those tend to be darker in color. This is Stone Mountain. It's located east of Atlanta, Georgia, where I grew up. So I've been to this place many times. It's a huge granite rock poking out of the ground. And I forget the guy's name, a sculptor wanted to pay tribute to heroes Southern heroes of the Civil War. So he got permission to carve these figures out of the face of the rock. Right? This is light colored rock, means high in silica. And it is granite. In fact, there's a lot of granite in Georgia. Some of the curbs on the streets are made of granite blocks. And the thing you don't want to do is ride up over one of them because they have sharp edges and they can cut your tires. But once you lay them down, they're going to be there for a long time. They erode very slowly. This is dark volcanic basalt, low in silica, high in those other minerals. All right, what about density and composition? The low silica rocks are more dense than the light colored silica rocks, which means basalt is denser than granite. Right? Granite's a high silica, basalt is a low silica, which makes it more dense. Now, these are relative terms, right? They're still a lot denser than water, but relative to one another, granite's lighter, basalt is heavier. Now, this is important for understanding things about what are the continents made of in general, what are the oceans made up in general. Dark, low silica rocks are more dense. Continental plates are composed of the less dense, high silica rocks. That's why they tend to float. They're higher on the surface of the earth than high density basaltic rock, which tends to be at the bottom of the oceans or underneath the crustal plates. Okay, so there's a difference between the continental plates and the oceanic plates that we mentioned in chapter 21. Oceanic plates tend to be denser, the low silica basaltics, and the continental plates tend to be the granitic types, the high silica rocks. Then there's the middle ground, andesite, medium silica content. Right? So this table puts it all together in terms of how we organize igneous rocks. High silica, low silica, light color high, dark color low silica. Granites, this rhyolite is extrusive rock. Intrusive rock is granite. And where you're likely to find them. Continental crust, oceanic crust, mediums, volcanic islands, and some continental mountain chains will tend to be in the middle somewhere. Okay, terminology again. What's a pluton? A pluton is an intrusive igneous rock. Forms below the Earth's surface by definition, and it's solidified magnet. So a pluton would be any intrusion on a localized scale, right? It's relatively small as rock forms go, right? On the neighborhood of only a few kilometers wide, no more. The size of the pluton and its shape help us classify these intrusive rock bodies. And we also want to, now we're starting to relate different rock forms to each other as they sit in their natural forms. So these plutons are in relationship to other rocks around them. These intrusive rock bodies are surrounded by other rocks that they have penetrated. And they're of a certain size and shape. Okay. If the pluton, during its intrusion, has cut across the grain or layering of surrounding rocks. So you say you have sedimentary rock overhead, right? It's in layers. And here comes this magma. There's the surface of the earth, this magma, and it pushes up like that. Pushes it out of the way and solidifies. This is discordant, a discordant pluton, because it cuts across grains of the overlying rock. Here's another term that we haven't defined yet. Batholiths and dikes. We will have to define those. But those are types of discordant igneous bodies. If the pluton is concordant, then it runs parallel to the grains or laying of the rock. So if it comes in like this, and it tends to, right, it does that, and sort of fits itself into the layering. That's concordant. Con meaning together and dis meaning apart. So discordant cuts across the grains, concordant fits in the grain. Layering. These are classified as either sills or laccoliths. Those are concordant bodies. Now we've used words here that we haven't defined. We need to define them here in a minute or two. So here's another picture of Stone Mountain. And it's a big rock. You can actually hike to the top. I did it once. It's a long, it takes several hours. It's all uphill. Here's another intrusive igneous rock, Devil's Tower in Wyoming. Right. One belief is that it was the central structure of a volcano, and the feedstock for the volcano underneath the magma settled down, and it cooled over time, and then the outer layers were eroded away and left this in the middle. Notice this angular structure here. Right. That's typical of basalt. Actually, it's not dark enough for that, is it? Okay, maybe I misspoke. Don't hold me to that one. Okay, so in this diagram, we see various types of igneous structures. Right? This dike is discordant, right? It cuts across layers of overlying rock. This batholith, also lith referring to rock, cuts across layers. The difference is that the batholith is huge. Batholiths usually cover hundreds of kilometers big, and each batholith may present various plutons coming off of it, right? So here's the formation of possible pluton there. Here's a laccolith, which is a concordant igneous rock, right? It's got a layering here and layering there, and it fit between them. There's another dike. Here's another laccolith, was exposed by erosion. All right. So again, the batholith is a large, exposed, discordant, intrusive igneous body, just like it showed in the picture. Large, very large, on the order of square miles. They typically are crystallized at depth very slowly. And at the surface, they're only exposed if eroded or pushed up, right? Other geologic forces may push them up, but you still have to have erosion to free them of the overburden. The pluton and the batholiths form from the same process, but the pluton is smaller. And several plutons may, like I said, may emerge from a single batholith. All right, so here's a pluton in the Sierra Nevada. Well, actually, the batholith is this whole area, and you can see individual pokies on them, which I would consider to be plutons. Right? A dike is a discordant, intrusive igneous body formed from magma that filled a vertical or nearly vertical fracture. So they typically, as a liquid, they flow into areas of the least resistance. So if some other geologic process has caused a fracture in the overlying rock, and you've got magma underneath, that it may be forced up into that crack. It may push the crack further apart, but it fills the crack. That's a dike. Okay. There's no one size or extent for these individual dikes. It all depends on the nature of the fracture that they're pushed into. Here's a dike that was exposed in Colorado. The dike tends to be more resistant to weathering than the surrounding rock. My guess is the surrounding rock was probably metamorphic. Sedimentary. And the dike was pushed up into the sedimentary. It's a harder rock, and the weathering just removed the overburden in the surrounding rock and left this dike exposed. Okay, sills are similar to dikes, except they're with the layering. They're on their sides. And you can get fracturing between layers of sedimentary rock, but that makes them concordant with the layering of the rock. Let's see, what's the difference between sills and laccoliths? Sills tend to be narrower, and they're injected between these pre-existing rock layers, whereas laccoliths are also concordant, and they are injected between the layers of pre-existing rocks, but they tend to be larger and push the layers apart. And sometimes this very hot, pressurized molten rock, magma, will cause a noticeable surface change to the overlying rock layers, a blistering, so to speak. Blistering referring to bulging up. So it may be higher on the top than it is on the bottom. That's the blistering effect, right? Everybody's had a blister somewhere or other. It tends to bulge up and eventually it'll pop. Well, the rocks don't do that, typically. Okay, here's an exposed laccolith. And you see it's blistered up in Wyoming. Okay, my plan was to stop this recording at this point. We're about the halfway point, so that you as a student could break and come back to the second part in a separate video. So that's what I'm going to do. I'm going to stop this one and I'll restart the second part. And you'll be able to find the second one in the same folder that you find the link for the first one. It's just that this makes it easier to logically separate one from the other. I'll be back in part 2 shortly.